Okay, so I think we are set. It's my very pleasure to have Dr. John Rushby from SRI to visit us and give a talk on must assurance be indefeasible. So John is the program director of SRI for formal methods and software dependability, and then he's well known for his research work on PDS and the development of assurance cases. And he is the I just want to read this one. He is the recipient of the 2011 Harlan D. Mills Award for practical and fundamental contributions to software and hardware reliability, with seminal contributions to computer security, fault tolerance, and formal methods. So I would just like to leave the rest of time to John, and then we are looking forward to the talk.
Okay, thank you, Ji-Hong. So I apologize for sitting down. I'm an old man, and this will work best for all of us. And it's a pleasure to see you here the day after Corpus Christi, when most of the country has taken the long weekend. So I'm going to talk about assurance and the strange word indefeasible. You can maybe guess what it means, but I will introduce it a bit later on. And this is the plan. I think there's a pretty good explanation available now for how assurance works for conventional systems, by which I mean modern aeroplanes, civil aeroplanes. And that connects up with this notion of justified belief and the possibility that that requires indefeasibility, which I will explain. And I will then talk about how assurance cases can or perhaps should be structured to give us indefeasible confidence. And then I will talk a little about the challenges of the future for systems like automated driving. And as we know from earlier discussions, that's a much harder problem, and maybe everything I've said before is irrelevant. And so we have to decide how much of that can we keep when we move to these new systems. So what we want from assurance is confidence. Well-placed confidence that our system does what we want it to do, but also does not do really bad things. So in the case of an aeroplane, it does not crash. And what you generally want is extremely high confidence that really bad things will not happen. And that is really quite challenging because of the probabilities and the numbers that are involved. So what the law says in both Europe and the United States is that for airplane software, there must be no catastrophic failure in the entire lifetime of all airplanes of one type. Okay? No failure, basically, no catastrophic failure. Catastrophic one is one which will crash the plane. And so if you just do some arithmetic, look at, say, the Airbus A320 series of planes. Already, they have flown 62 million flight hours. And so at the end of their lifetime, in maybe 30, 50 years' time, they are quite likely to have flown many times 10 to the 8, maybe even 10 to the 9 flight hours. And if there's to be no catastrophic failure, that's a probability of failure of 10 to the minus 9. Okay. 1 in a billion. And also, the quote at the bottom is from some of the guidance documents on assurance for airplanes. And it says you can use 10 to the minus 9 as a guide to engineering judgment. An extreme number, 1 chance in a billion that you will have a failure. But the amazing thing is that what's done at present seems to work. And until fairly recently, there was no really good explanation for how or why it works. Now I think there is quite a good one. So what is actually done? Well, people apply these standards in aeroplanes. It's things like DO 178, it was B, now C. ARP, Aerospace Recommended Practice 4754, 54A. These are documents that what they require you to do is apply extreme care and extreme scrutiny to the software that you develop. So what is actually accomplished by this extreme care? Well, the interpretation that seems to work is it gives you confidence that the software is fault-free. It contains no faults at all. Now, there's a variant theory that's more complicated, but perhaps more credible, that says it's got a very low probability of failure, but I'll stick with the simple theory, okay? Which is good enough. And so if we have software that is with strong confidence, free of faults, it will never fail, right? Failures only occur if you have a fault. And so the fault is the thing that is wrong with your software, and the failure is a departure from desired behavior. So we could express our confidence in fault-freeness as a probability. And we write it as P sub NF. Okay? And it's a subjective probability. It tells you how confident you are, in your heart, that the software is free of faults. Some people find that very hard to accept. You can give it a frequentist interpretation by saying, suppose we build many, many pieces of software this way, all to the same kinds of standards and the same kinds of requirements. How many of them would ever see a failure? Okay, and that would be the same number. Now, I think it's pretty clear that you cannot get a big number out of probability of no faults. Maybe 90% confident, 50% confidence, 90% confidence. You can't get 10 to the minus 9, no, 10 to the 9 confidence. Okay, and so it seems difficult to figure out how do we connect this fairly good confidence that there are no faults with extreme confidence that there are no failures. I think there seems to be a disconnect. And the crucial thing is this little equation here, the 1. So we need another bit of notation. If the software, despite our confidence that it's fault-free, does contain faults, we want to know what's the probability that it will fail given that it's faulty. Okay, and that's this notation p big F sub little f. Okay, probability of failure if faulty. And what we then want to calculate is what's the probability of surviving, long-term survival, okay, n demands, and we could take a demand to be a flight hour. So what's the probability of surviving n flight hours? Well, if there are no faults, we're good, okay? So probability of no faultiness, that gets us going, and then we have to add on whatever happens if we are mistaken about it being non-faulty. Okay, so we add on the product of the probability that it is faulty, 1 minus p sub nf, multiplied by the probability that it doesn't fail, given that it's faulty, 1 minus p big F little f, raised to the power n, which is our number of demands. Okay, so pretty simple and unarguable. Now, what's interesting about this is that if that first term, p nf, probability of non-failure, is reasonably large, fair, like 90%, it looks like we're done. Okay, all we want is confidence that we're going to survive n flights, and we're there. Well, the problem, of course, is that our confidence might be misplaced. We are 90% confident that there are no faults, but there's a 1 in 10 chance that there is. And so what we then need to be sure of is that that second term will be well above 0, okay, and will be our backstop. Well, the trouble with that is that power to the n, okay, where n is a billion. Any number, no matter how close it is to 1, when you raise it to the power of billion, is 0, okay? And so how can we get something useful out of that last number, that last term? Well, one possibility is that we can do it by basing our confidence on prior failure-free operation. And then it becomes a problem of Bayesian estimation. What's happened is that we have seen some number of, I need to get my glasses on here. We need to get some, we have our hand on heart estimate that there are no failures, probably P and P sub F. And then we've observed some number of failure-free flights, okay? Maybe flight tests, R. And we want to know what's the probability of seeing n failure-free flights, in other words, another n minus R. And if you set that up as a Bayesian estimation problem, you need some prior estimate for the probability of failure if faulty. It's really hard to see how you could get any number that you could put in there, or any probability distribution that you could put in there. It'd be very hard to find and even harder to justify. And the breakthrough was the discovery or the invention that there is a worst case. There is a certain probability distribution that is provably the worst case, and it's one that sticks all the probability mass at one particularly bad place. Okay? And what you can then demonstrate is that you get a useful number that's guaranteed to be conservative, okay? Given only these 3 parameters at the bottom. Probability of non-faultiness, which we get from our hand on our heart, R, which is the number of failure-free flights we've seen, and N, the number that we need. Okay. And the way it works out is that provided, with our hand on our heart, we think there's 90% confidence in probability of no faults, then that second term is well above 0, provided R is above about n over 10. So that looks interesting, but not good enough, because we want 10 to the 9 flight hours, and it looks as if we need to have flown 10 to the 7 before we're going to be confident of 10 to the 9. But we don't build all the planes and fly all the hours all at once, right? Bang. What we do is we build 5, 10 planes a month, and they fly so many hours a month. Okay? So at the beginning, you've only got a few planes, and you're only flying a small amount, and you've done a lot of flight tests. So as long as the flight tests are good enough to be 1/10 of the number of flight hours you want to guarantee, you're in business. And then 6 months later, you build some more planes, you've got more flight hours, but you've seen more failure-free flights. Okay? And so you work your way forward, basing your confidence in the failure-free operation of the fleet on what you have seen so far, all driven by the fact that you have confidence that there are no faults. Okay? So this is a calculation that was done by Strigini and Pavliako at City University. And I think it's a really neat model. What's the breakthrough? Because it explains for the first time how it all hangs together. Okay? And it's consistent with practice. I was once in a meeting with a person who certified an actual aeroplane. And she said she probably wouldn't fly it for a year or two, even though it was her signature on the certificate. So there's a certain amount of confidence you have at the start, and you maintain it and develop it as
so personally, he wouldn't get into the plane.
Sorry?
He personally wouldn't get into the plane that he's certified.
That's right.
Okay.
But confidence development, that's an extreme case perhaps, and not perhaps one that we want to dwell on. But the basic point is, you start off with confidence and you develop and increase it in a way that is adequate to get you to this justified belief, that in the end you will be failure-free for the lifetime of the fleet. And of course it is the case that sometimes you do see a failure or some problem. You can think of the 787 battery problems. There they grounded the fleet, okay, and fixed it. And there are additional probabilistic models that calculate the effectiveness of detecting things before they become a failure, detecting incipient signs of faults, and maybe keeping the fleet flying, but still fixing it at some point. And even though you're flying a plane with known potential failures, again, you have enough probabilistic guarantees that you're okay and you will fix it. And good probabilistic models for doing this.
So you make this innocuous assumption of independent authority demands.
That's
doing these billions and billions of dependencies that are out there, right? You're doing that abstraction.
That's true. I mean, there are some planes that get into extreme circumstances, which have never been seen before. There have been planes that have been inverted, for example, by getting into the wing vortex of another plane. All bets are off in that circumstance, but the plane is part of a larger system that is trying to prevent that ever happening. Okay, you'd never fly too close to the wing vortices of a bigger plane. That's why they have a 1 or 2 minute gap after a heavy plane takes off before the next plane takes off. And so, the idea is that you've seen all of the expected and representative behavior. You rule out the extreme behavior by trained pilots, managed airspace, lots of other sort of system level attentions to detail, and you're fairly confident of where you are. So, as I say, it seems to work. There have been no airplane crashes due to software, okay, and relatively few things would even count as an incident. Okay, and most of those are attributed actually to faulty requirements. It sounds like quibbling, but there is a distinction between the way one assures that the requirements are correct and the way one assures that the software is correct. So, there's a probabilistic model that says this is how assurance works, and it does work. Okay? But to get the process started, you've got to have a reasonably good confidence in the absence of faults, a total absence of faults. Okay, probability of confidence, probably say greater than 90%. So how do we get there? Well, the modern idea is one uses assurance cases, and I'll talk about those shortly. But the question is, how does one actually attach a number to the assurance that comes out of an assurance case? And what is it that you're actually trying to achieve? Well, as I mentioned, what we're trying to establish is confidence. Okay, and sort of somewhat elusive notion, but one idea is that what confidence is justified belief. Okay? Belief in a property that has good support for believing it. Now, the limit of justified belief would be justified true belief that really is true. And justified true belief is a traditional definition of knowledge. Okay? It goes back to Plato and I think the Timaeus. Okay? So 2,400-year-old notion of what is knowledge. And so another way of looking at it is to say we want to know that the software has no faults. And that takes us off into the world of epistemology, the philosophical study of knowledge. And as I mentioned, for 2,400 years, Plato's account was pretty well accepted. Justified true belief does the job. But then Bertrand Russell in 2012 posed what's sometimes called the stopped clock case. So, our hero Alice goes out and looks at the clock on the church steeple, and it says 2 o'clock. And so she believes that the time is indeed 2 o'clock. And it turns out it is 2 o'clock. But, unknown to her, that clock is stopped. But it's stopped exactly 12 hours ago. So she has justified true belief. But should we count it as knowledge? So the problem is, she was lucky that her belief was true. Her belief is justified. I mean, she looked at a clock. Okay? That's a way of gaining confidence, that you know what the time is. But she failed to account for the fact that clocks sometimes fail. So she had a poorly justified belief that happened to be true by accident. And so what this suggests is that justified true belief isn't actually the right definition for knowledge. And so people knew about this from Russell onwards, but it didn't attract a lot of attention until a guy called Gettier published a paper in, when was it, 1963. It's a 3-page paper. So he was a professor of philosophy at university, and he hadn't written any papers. And his colleagues said to him, you're not going to get tenure, even here, wherever he was, without having some published work. Okay, so he wrote up what he had, 3-page paper. It's now the most widely cited paper in epistemology. It has over 3,000 citations. He never wrote another paper. Okay? And what it does is it gives you, I think, 2 or maybe 3 more stop clock kinds of examples. Scenarios where someone has justified true belief, but it doesn't really count as knowledge because their belief was true by accident. Okay? And they're crazy examples. And the other 3,000 papers invent even more crazy scenarios. Okay? It's really bizarre, some of them. But the basic point is that it seems clear that we've somehow got to beef up our notion of justified true belief. And it also seems, from my point of view at least, that the problem is our notion of justification is too weak. Okay? In Alice's case, she didn't consider the possibility of the faulty clock. And so if you'd asked Alice to give you an assurance case for why the time is 2 o'clock, you would have said that's not a good case. You haven't thought of the possibility that the clock is faulty. The clock is stopped. And so what modern work on epistemology does, apart from inventing silly cases, is propose adjustments and alternatives to justify true belief. One of the adjustments that I think is a good one is to propose that it's not enough for your belief to be justified, it has to be justified indefeasibly. And what that means is you're so confident that you have looked at all the reasons why your belief might be false that you cannot imagine any new information that would make you change your mind. Okay, that's what indefeasible means. It comes from defeasible logic, okay, non-monotonic logic.
So, okay. So that means that, for example, for certification of flights, that you not only should say that it is the same, but you say that there is no other way that you can imagine to.
That's exactly right. You basically have to say you have thought of everything. There's no scenario that either you or nature could come up with that I haven't taken into consideration. Now, I can't know that, but I have to have strong confidence in that. I have to be really confident that I've thought of everything. Okay? And what I want to claim is that's what our goal has to be. And it's somewhat close to what is achieved, and I'll explain how in a minute. But that's indefeasibility, okay? You thought so carefully about everything that there's nothing left over. Okay? So whenever there's an accident, the press says they didn't test it enough. Okay, and that's because the press thinks the only way of finding failures and faults is by testing. Okay? The real way you find failures and faults is by thinking. You anticipate the circumstances. You look at what happened in the past. Okay? You do model checking. You do a lot of stuff. Okay? And you have to have done enough stuff that there's nothing left over. Okay? So, the epistemologists worry about knowledge. Okay? I think that's actually the wrong thing to worry about, because only the omniscient can know what is true. The best we can do is really well justified belief. Okay? That's to say, indefeasibly justified belief. And so that's what we should take as our criteria for assurance. And there's a quote at the bottom, "What you don't know can't hurt you." It's the title of a paper in this space. Okay? And that's really what it has to sums it up. You have to be so confident you thought of everything. Things you haven't thought about must be, you know, variants on things that you have, and they have to be in the noise. What you don't know can't hurt you. So the way we are going to achieve indefeasible confidence is through assurance cases. I think everyone here knows what they are, but basic idea is you have an argument, and you want to make it a structured argument. And the usual way is to present the argument as a tree, where you have claims. Things like the boxes are claims, the rectangles are claims. So we have a top-level claim, the plane is safe. And then we have a lower-level subclaim, the software has been adequately tested. Okay? And at the bottom, we have evidence, things that we have actually looked at, either in the world or in our software, which are things we've done. And connecting them, we have these rhomboids, which are the assurance steps that explain why it is that this bit of evidence gives us this subclaim, and this bit of evidence and that subclaim gives us that claim. Okay, that's the idea. And what you do is you build a tree like that with 5,000 nodes. Okay, it's an aeroplane, it's a vast tree. And ideally, you can gain confidence in the top node by gaining confidence in the individual nodes. It's a divide and conquer strategy. Okay, and again, we'll see how we can achieve that in a bit. So, the example could be the top-level claim is that the software is correct, and then E2 could be test results, and E3 could be how the tests were done. Okay, so E2 would be, we did 5,000 tests, and all of them were passed. E3 would say, why did you choose those 5,000 tests? How did you know that your test oracle is correct? Okay, so all the other stuff you might want to worry about. Subclaim 1 would then be the software was adequately tested. But then that might not matter if you tested the wrong software. If the software that's on the plane is different than the software you tested. And so you need some other claim buttressing that, which said, the version management was good. And that's what the upper bit of argument might be. And E1 might be evidence of how you did version management. So you know that what's on the plane is what was tested. Okay. So, applying the indefeasibility criteria. So, there's two ways in which an assurance case could fail. One is that our evidence could be weak. So if we go back here, it might be that we didn't do very many tests, and therefore the purpose of tests in assurance is not to find faults, it's to provide evidence for the absence of faults. Okay? So the more tests you do, if you ever find a fault when you're testing for this purpose, it's a catastrophe. You don't expect that to happen. But you do more and more tests, still not finding faults, and that increases your confidence, okay, that there are no faults. So it may be that you didn't do very many faults, and therefore the strongest confidence you can have in subclaim 1 is moderate, it's fairly low. Okay? And so that's one way in which your assurance case could be inadequate. Your evidence could be weak. But I would argue that is something that we manage probabilistically. We're in the world of confidence, experiment, so I'll come to that in a bit, but can be managed. The other thing that could go wrong is that our argument is basically the wrong argument. There's something missing, okay, something we didn't think of. And that's sort of catastrophic in that there's no probabilistic assurance you can give that. And so what can go wrong? Well, you can have a hazard. That's to say there's some situation in the world or in the system that could cause it to fail that you haven't thought of. Or you could have what's called a defeater, which is like a hazard to the argument. There's some reason why the argument doesn't hang together. The system might be okay, but the argument isn't. Okay? So a hazard is a fault in the system, a defeater is a fault in the argument. Okay? And so if you have either a hazard or a defeater, then Mother Nature might find it and cause you to fail. And there's really no way of fixing that. Okay? If you've got either a hazard or a defeater, your confidence in the overall case has to collapse. And so there's no way of managing it. And so what indefeasibility is about is saying you cannot have those. Okay? And there's a reason you cannot have them, is that it really is bad if you do. Okay? So what's going on here is that most people who work on insurance cases sort of agree with this. Not completely, but sort of agree with it. But they do it by a sort of a bottom-up justification. And what's new about this indefeasibility story is it's a top-down justification. It comes at you from the world of epistemology. So of course the big question people ask is indefeasibility realistic? So, we can repeat the argument why you need it. If you've got a defeasible case, you've got a hole, you've got a hazard or a defeater. And that hole is of unknown size, okay, because you don't know anything about it. If you knew about it, you would have fixed it. And so there's a gap there, and who knows what significance it could have. Indefeasibility says you must have no gaps. So how can you do that? How can you guarantee that there are no gaps? How can you guarantee that you've found all the hazards? Well, how is it actually done in practice? You do hazard analysis. That's to say there are these systematic methods for trying to think of everything that can go wrong. Different industries have different approaches. Most industries use multiple approaches. Typical ones are things like HAZOP. You think of the flow of data through the system as if it's fluids through a pipe. And then you say, what if this one is too late, or this one is too slow, this one is small, this one is large? Okay? You systematically explore all of the cases. And so when you've done hazard analysis, you've found, you hope, all the hazards, in what's called a hazard log. And you've got evidence that you've found them all. The evidence is how you did hazard analysis. I used this approach, it's the standard, it's recognized as being okay, I did it really thoroughly. Here's our description of how we did it. We had good people, and ... And so what I've got is evidence that I did hazard analysis really well. And so what we've really done is we've transformed the possibility of a gap into evidence that there is no gap. Okay? The evidence for having done hazard analysis really well gives you confidence that there are no hazards. Okay? It sounds like a sophistical trick, okay? Playing with words. But it's not. If you asked, how could I have gone wrong? How could I be defeated? How could it be defeasible? I would have to have made an error in my hazard analysis. And I've given you evidence that I haven't. Okay? And of course, that evidence might be weak, back in the other case.
So now if for people who build this assurance case, they don't consider hazard analysis as a way to do it, or? Hazard analysis is the sort of foundation for what they do, but they don't build it into the case in the way that I'm advocating. The most famous failure of an assurance case is the British Nimrod, where they were adding some capabilities. I think it was air-to-air refueling. And the case turned out to be flawed. The plane crashed and everyone died. And there was a court case, an inquiry by a judge who looked into it and found that the assurance case was essentially worthless. They had done a pretty good hazard analysis and had a good hazard log, but they then, for no good reason, sort of struck off some of the hazards and decided not to explore them. Actually, we're halfway through. Let me tell you a joke. The guy who
this inquiry for the British government was a very senior judge. And as a senior judge, he gets to go to lunch and dinner with the great and the mighty of England, including the royal family. So apparently he's there at lunch, shall we say, with a member of the royal family, and he says, "What do you do, Mr. Haddon Cave?" And he says, "I'm a judge." "Oh," she says, "how nice. Dogs or horses?" You have to know about British life, maybe, to understand that one. Okay, so we now know that there are plausible ways of being confident that we have no gaps, that we have an indefeasible argument. And now we have to ask ourselves, how do we actually analyze an assurance case to gain confidence in it? What should we actually do? So it's much easier if assurance cases have a certain form, which I call simple form. Okay. So on the left, we have the assurance case we saw before, and you notice that the top box has a step, and underneath it is both a circle and a box. It's depending on some evidence and a subclaim. Whereas the other bit of the argument, you have a box depending on two circles. Okay? It's really much simpler if you only have two kinds of shape. Boxes depending on boxes, and boxes depending on circles, never the mixture. And you can always create that by, if necessary, inserting extra nodes. Okay? So the idea is that in a simple assurance case, you only have either subcases like this, where you've got a box dependent upon circles, and that's called an evidential step, because the circles represent evidence. And so you've got a subclaim supported by evidence, and the same here. Or you have a box supported by boxes, like the upper triangle, and that's called a reasoning step, because your subclaims are logical statements. And so it's not actually necessary to have this form. It's much easier to understand things if you do. And the reason is that I think it's a really good idea to interpret two different kinds of step differently. The evidential steps, the ones that have got circles at the bottom, they're about epistemology. They're about what do I know about the world. And so the way in which we decide if we have enough evidence to support a subclaim is we've somehow got to amalgamate all the different bits of evidence that we have and achieve some confidence. And that's a sort of I'll talk about it in a minute, not a logical thing, it's an epistemological thing. You've got to somehow weigh the evidence. You can't just sort of conjoin it all together. Okay? You've got to weigh it. And I'll talk in a minute about how we do the weighing. The reasoning steps, we've got subclaims, which are logical statements, supporting a higher level subclaim of the logical statement. And that's logic. It's reasoning. Okay? So reasoning steps are about logic. And the idea is that we apply our epistemological methods to all of the evidential steps and assure ourselves that each of the subclaims supported by evidence has passed some threshold. The evidence is good enough. Yeah? Tick them. And then once all those subclaims are ticked, they've crossed their threshold, we treat them as if they're valid premises in a classical logical argument. Okay? And the rest of the argument is just logic. Okay? Treat the premises as premises. And so this is actually, turns out to be a systematic treatment of a style of argument known as natural language deductivism. Okay, I didn't know that until very recently, and Robin Bloomfield, a friend of mine, went to a conference of people who do what's called argumentation. They're sort of a different group of people who study very similar problems from an entirely different point of view. And they call this approach natural language deductivism. So when I grew up in England, and when I was a kid, you learned French as your foreign language. And so at the age of 16, I could read Molière. And there's a character in Molière who's amazed to discover that he's been speaking prose all his life. He says, when I say, Nicole, bring me my slippers, I've been speaking prose? Yes, sir. Okay, he's amazed. And so I'm amazed to discover that I've been doing natural language deductivism.
So just a quick question. So for this natural language deductivism, so that means that if you want, for example, to advocate it to avionics, to establish this claim, it's not totally difficult because they build up they just try to rearrange their things.
I would hope so.
Okay.
you'll notice what's going on here is our notion of assurance case is actually getting simpler. We don't have all of the, well, we'll see in a minute, we do in some cases, have what they call confidence claims and all this other complexity you find in. So how do we weigh the evidential steps? So the problem is that you can't treat the evidence as bits of logic because they might not be independent. You know? You're trying to observe something about the world, you know, like correctness of software, that you can't observe directly. Okay? And so you make indirect measurements. You know, you do static analysis, you do testing, you look at the quality of the code, you eyeball it. You know? And these are all indirect ways of trying to judge the quality, the correctness of a piece of software. But they're not independent, and so you can't say this, you know, plus this or times this. You have to somehow amalgamate them. And so the term that's used is weighing the evidence. Okay, it comes from the notions of court of law. You weigh the evidence, and there are ways of doing this using Bayesian methods, in particular BBNs, Bayesian belief nets. And these methods can deal with complexities such as Jihong and I just alluded to, like confidence measures. And I'll give an example in a moment. So the question is, what is the probabilistic notion that one should deal with? It might seem obvious that what you want is the probability of the claim given the evidence. Okay? That seems to be what you want. But this is really hard to estimate. Even experts find it really hard to come up with any kind of number. You know, is it bigger than a half or less than a half? I don't know. Okay? Not only that, but if you do any kind of Bayesian estimation, it's going to depend upon your prior. Okay? And your prior is the raw probability of the claim, okay? Which you don't really have any right to have. And if you interpret this as being in a court of law, it's prejudice. Okay? And so it turns out it's much better to turn it around and to look for the probability of evidence given the claim. Okay? And it's intuitively reasonable. If I say, here's the evidence, what's the probability the world is like this? That's quite difficult. If I do it the other way around and say, if the world is like this, what's the probability you see this evidence? That's an easier mental calculation to do. Okay. And so there's a lot of value in just turning it around. But in addition, you want something more than that. I don't want to know what's the probability of the evidence given the claim, but how good is the evidence at distinguishing the claim from the failure of the claim? Okay? It could be, for example, that the evidence is totally unconnected to the claim. It might be a tautology. Okay? And so what I want is something that connects evidence given the claim from evidence given the negation of the claim. Well, these are probabilities, so you can take their difference or their ratio, or take their logs. And people do all of those, and you get these different measures, okay? It doesn't matter which one you use, really. They're all called confirmation measures, and they come from the world of Bayesian epistemology. Okay? There's a whole literature on them. And the simplest one is what's called Good's measure. Good was a guy who worked with Turing on the code-breaking activity during the Second World War. It's pretty old stuff. Okay, so it doesn't matter which one you choose, but a measure like that is a good one. We want to look at our evidence and ask, does it help us discriminate between the claim being true and the claim being false, rather than just the claim being true? Okay? And by the way, there's an interesting paper by a guy called Gardner-Medwin saying this is what juries should think about in a court of law. You should tell them not to try and figure out if the evidence convicts the guy, but whether you could have seen that evidence if he was innocent versus whether you would have seen it if he's guilty. And it also tells you what the defense counsel should do. They should try to justify how you could see that evidence given innocence. It's quite an interesting line of argument. So I don't think you need to actually play with the numbers. You just need to understand this stuff and sort of apply it intuitively. But it is actually quite valuable to do some what-if experiments. It helps you get your intuition going. And so one particular example you see is NDL178C, where you've got about 80 different things you have to do to finish your assurance. There are things like this one at the bottom. Assure that each high-level requirement is accurate and ambiguous and sufficiently detailed, and that the requirements do not conflict with each other. You think, what is that doing? You know, what's the value of that? Well, you can build a BBN. So So this picture at the top left is a BBN, and the idea of Bayesian belief nets is you've got many different random variables that are not independent. And so calculating, what happens to the one you care about when you whittle this one, really hard calculation. But usually the dependencies are quite sparse. And so the idea of a BBN is you assume that they're not there unless you draw an arrow. Okay? So an arrow tells you where there are dependencies. And so the idea of this diagram is that we're trying to combine testing evidence with verification evidence. The only bit that matters is the top left-hand corner, which I'm going to look at. So what we have is the top letter Z or Z, and the idea is that that's the system specification. Actually, it's a random variable, is the probability of the system specification being correct. Down below it, dependent upon it, we have S, the system, actually the probability that the system is correct. And then dependent upon that, we have T, the test results. Well, the test results don't just depend upon whether the system is correct, they depend upon whether the oracle is telling us, the thing that you use to judge whether a test is passed or not. And the oracle is derived from the spec. Okay, and so you have that little box up the top left. Ignore the blue one for a minute. And what you do is you type that into a tool. I'll show you a picture in a minute. And then you type in a box like this that says, if the system is correct and I've got a correct oracle, then it's guaranteed that my test results will pass, 100%. If I have a bad oracle, who knows? It's 50%. Coin flip. If I've got an incorrect system and a correct oracle, it's going to be pretty good. It's going to detect the failure, but some will sneak through, 5%. And if I've got a bad oracle, again, who knows? 30%. Make these numbers up, okay? And then you play with them. You go into a tool, this one's called Hugin, you get it for free, and you put the numbers in and you can play with them. If you click on one of the bars, it'll whack it over to 100% or back to 0. And you can really see what's going on. It's quite instructive. It's like playing with a spreadsheet. Okay? Now, one of the things you will learn in this particular example is that the value of the tests is highly dependent upon the quality of the oracle. Okay? Makes sense. But it's extremely hard to judge an oracle. So one thing you could do is you could judge the quality of the specification. You could say, is this a good spec? You could say, ensure blah, 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 this thing at the bottom. And what that would do is give you some judgment on the quality of the specification. I'm calling it A. And then the quality of the oracle would have some connection to that. Okay, so plug some numbers in, play with Hugin, and you learn stuff. Okay? And it's, as I mentioned, really quite instructive. And so it will guide you, I think, in deciding what kind of evidence you want and what sort of thresholds you should have. It's still, dependent upon your judgment. This helps you hone and refine your judgment. And if you look at what's in DO 178C, as I said, there are about 80 different things. It's not at all clear why they're there, what's connected to what. I think building some of these would be really instructive. So that's how we do evidential steps. Ultimately, it's a judgment with our hand on our heart, but we can develop our judgment by using these probabilistic experiments. And in the limit, you could actually do it that way, but just be very hard. So the evidential steps are weighed probabilistically, and when they cross some threshold, we treat them as premises, and then we do logic. Well, there's two kinds of logic we could do. We could do classical deductive logic, where if the premises are true, the conclusion is guaranteed. Or we could do what's confusingly called inductive logic, feasible logic, where if the premises are true, there's a strong chance that the conclusion is true. Okay? But we don't guarantee it. So there's lots of problems with the inductive approach, but that's the one that is standard in assurance cases today. If you use GSN, they're really basically advocating you do inductive logic. If the premise is true, I'm very confident in the claim, but I don't guarantee it. And there's all sorts of reasons why that's the wrong thing to do. And many of the reasons why it's wrong can be done by bottom-up reasoning, and here's one. It ain't modular. The reason it's not modular is that if you believe only that the premises suggest the conclusion, you're admitting there's a gap, there's something missing, but you don't know how big it is. And so either you're saying it doesn't matter, it's so small it doesn't matter, in which case it might as well be deductive, or you're saying it does matter and I've taken care of it somewhere else. Otherwise you're irresponsible. Okay? And so if you've taken care of it somewhere else, it's not modular. Okay? So that's a bottom-up kind of justification for why you don't want inductive reasoning. But the justification I prefer is the one that comes from indefeasibility. It says that our goal is indefeasibility. We must have thought of everything, and that means our reasoning steps have to be deductive. If this is true and this is true and that is true, then that has to be true. And then we could ask, what is our overall confidence in the case, right at the top. Well, you could actually try to play with probabilities. You could assess a probabilistic confidence in each evidential step, and then you can multiply them together, because the upper ones are assumed independent. Okay? But it's pretty hard to justify that and pretty hard to get the numbers. I think what you should do is just assert it. We say that if our thresholds are good enough on the evidential case, on the evidential steps, okay, and our reasoning steps are indefeasible, then bang, the top one is, above our threshold. Okay. Now, that sounds good, but there's a problem at the bottom here in red, graduated assurance. So I've been talking as if everything is supercritical. It could cause a catastrophic failure. But there's lots of software on an aeroplane, and they have different levels of criticality. And you don't want to do really thorough, expensive stuff on less critical software. And so they have a dial that they can turn. There's what's called level A software, which is where you do everything. Level B, level C, level D, all the way down to level E. And you want to somehow find a way of reducing your confidence and making it cheaper without losing everything. So what can you do? Well, you could eliminate some subclaims. You say, I just don't care about this. I say you shouldn't do that, because that lets defeasibility in. Okay, and even for the weaker claims, I think you should still try to think of everything. And so you can't take a case for the most critical software and simplify it by chopping stuff out. Okay, so what else can you do? Well, you can lower the thresholds on the evidence. I don't need so many tests. Okay, and you might say, I'm going to take away some evidence. At one level, you might have testing and static analysis. And you say, for less critical software, I don't bother with static analysis. Okay? That's fair enough. That's not taking indefeasibility away. It's reducing a threshold on evidence. And if I don't need static analysis, then I can take a whole chunk away, because I don't need to worry about the soundness of the analyzer. Okay? So if I take away some evidence, then I can take away some entire parts of the subtree. It's for a different reason than just a priori pulling them away. So I think there's a way of doing it here. And this is a valid way of creating a dial. So what we're left with is, how can we judge that an assurance case is good? Okay. So you can look at the evidence and the thresholds. That, I think, is a fairly systematic thing. You maybe invite people to play with your BBNs. But the thing you have to really worry about is this notion of confirmation bias. That's what the Nimrod people had. That's to say, we tend as humans to believe our own propaganda. We tell a story and we believe it. And the only way of really challenging that is to have other people come in. They're very good at finding holes in your argument that you can't find. So you have to have a dialectical challenge, a debate with other people, strong critics. And their task, I would say, is to look for defeaters. That's to say, hazards in the argument, reasons why the argument will go. What if this isn't true? What if that happens? Okay? And what we want to do is to record those challenges. The assurance case should somehow capture those, so that when you make a modification or build a variant, or somebody comes back in a year's time, you've got all that existing dialogue already there. You don't have to rediscover it or revisit it. And so somehow or other you've got to find a way of feeding that in. And I think there are ways of doing that. Not topic for today, but you basically want the dialectical challenge itself to be recorded as an assurance case, so that the same tools can evaluate it. And what that means is, although the final argument should be indefeasible, and therefore the reasoning that goes on is deductive, while you're in the middle of a debate, of a dialectical challenge, you might have something you think is only inductive, that is at the moment defeasible. And so I think there's value in, although your ultimate test is deductive and indefeasible, during development you allow inductiveness and defeasibility. And so your tool should actually allow both kinds of justification and reasoning. And there are some that have done that. There's a Japanese tool called Ashtar. It's the most widely used case tool in Japan. And they have a version that supports GSN, I forget what GSN stands for, Goals Structuring Notation, which is a fairly standard notation for assurance cases, where they build in what's called Carneades-like capabilities. Carneades is one of these argumentation structures, notations from the world of argumentation. It's parallel work. So there's merit in this, I think. So, getting to the end now, just a few more slides. I think this is a pretty good story that tells us how the current methods work. We know they work. Until now, there wasn't really a good case for why they work. Okay? I think this explains why they work. Currently, they don't use assurance cases, they use standards, like DO-178C. But you could restructure those, and in fact, people are doing that as assurance cases. I think you could improve them, actually, using the methods I've described. But it works, and this explains why it works. As I mentioned earlier on in dialogue there with Chi-Hong, this notion of assurance case is really simple, okay? Much simpler and more strict than current notions of assurance case. You can build tools, I think, to support this really simply. So my personal opinion, it's only my opinion, is that if you started from scratch and built a new system and a new assurance case, it might not be reliable. The reason is confirmation bias, really hard to stamp that out. And so what I think is probably best is to have frameworks of cases that are widely accepted by the world at large. So those could be standards, reformulated as assurance cases, and I say there's work going on to do that. And you have to have been in these assurance cases, these standards committees to see how effective they are. There's a room full of people each with their axe to grind, and they're pretty good. If someone proposes something that's pretty weak, someone will shoot it down. Whereas that's not true if you're, with your own friends. An alternative would be to have patterns and guidelines for assurance cases. And I think, we could do all that, make the world a better place, guaranteed to work. But what about the distant future? Well, of course, it's not more distant anymore, it's imminent. And those are things like self-driving cars. In California, you already have Teslas driving around on autopilot. So the methods I've described and that seem to work all depend upon strong predictability. In fact, in an aeroplane, you're not allowed to have any non-determinism. Okay, so when a plane flies from warm, dense air at ground level to thin, cold air at altitude, the control laws have to change. It's completely different aerodynamic properties for those different kinds of conditions. And you could have a single adaptive control law that would do the whole thing. Not allowed. They'll typically have dozens of separate certified control laws that fade in and out as you move through the different levels. Not allowed to have non-determinism. So, the world we are hypothesizing of automated self-driving cars and so on, that has unpredictable elements to it. Our software could be unpredictable because we built it out of a learning-based vision system, for example. The external world is unpredictable. I was talking with Harold about how you guarantee you don't get into the downwash or the rotor of another aeroplane. Air traffic control guarantees you won't do that. On the road, no one's guaranteeing this, right? There's crazy people all around you. And so you don't have a predictable world and you don't have a predictable system. So what can we do? Well, one thing that helps us a little is that our goals are much lower. We typically want something like no worse than human. So in the United States each year there are 35,000 fatalities due to road crashes. That's quite a high number actually compared with Europe, even given the number of miles driven. And so there's a lot of opportunity there. Okay, you don't have to do all that well to do better than humans. So what's the future? What can we do for things like self-driving cars? Well, one would be to say retain indefeasibility. And then the problem is, how can you cope with unpredictability? Something's got to give, right? If you say, I'm going to think of everything, but the world is unpredictable, what can I do? Well, the only other dial I have is thresholds on evidence. Maybe I can drop that down very low. That doesn't seem to buy me very much. The alternative is to abandon indefeasibility. We say, the world is unknowable, and we can't think of everything. We'll just do the best we can, and we'll learn from experience. That's to say, we'll let people crash, and we'll figure out what went wrong, and we'll fix it. And that's better than people. You know, when people crash, that person learns a lesson. Okay? When a piece of software causes a crash, you fix the software and it will never happen again. Okay? So that's Tesla's argument. Neither of these seems particularly attractive, if you'll agree. So maybe there's a third way, and that's to use monitoring. So the idea would be, and this is purely speculative, I'm not a strong advocate of this, there may be better ideas, and I hope we can discuss them, is that if you have weaker properties, then weaker knowledge might suffice. And so even if strong knowledge is unpredictable, weak knowledge might be predictable. And so, there are certain circumstances where, if I can't drive the car the way I want to drive it, maybe there's some really cautious way of driving that isn't going to cause an accident and will at least get me to the side of the road. And I don't need strong knowledge, strong predictability to guarantee that creeping to the side of the road will work. And the idea of monitoring is to check whether the assumptions that your strong properties depend upon are being violated or not. Now, can you monitor for things like sensible behavior and for your own opaque software? Well, there are some imaginative ideas. One idea is, how can I monitor my own vision system? So the idea, which comes from Wilfried Steiner and others at TT Tech, is that, well, you've got a GPS in the car, you've got good maps, so you know where you are, and you can calculate what's in front of the car, the static things that are in front of the car. And you can say, well, there'll be a gas station on the left and a mailbox on the right. And you ask the vision system, do you see it? What do you see? It says, I see a gas station on the left and a mailbox on the right. Then you know that at least it's awake and interpreting the world reasonably accurately. You don't know that it's going to see the person in front of it, but you know something. Okay? So, you've monitored a weaker property. Maybe that gives you some help. So you've got monitoring that gives you some guarantees, and then you can build basically fail-safe architectures, what are called monitored architectures, where if an assumption is failed, you stop. Okay, you hand control back to the driver. The trouble is that there's pretty strong evidence that doesn't work. So one example would be Air France 447. That was the crash of the plane going from Rio to Paris, where the pitot tubes froze up, they lost air data, the autopilot says to the pilots, your aeroplane, okay, and they then proceeded to crash the airplane. If they'd sat back and had a beer, that plane would have recovered actually in the end, but it didn't work. And so the alternative is what is sometimes called a simplex architecture, a crazy name, but that's the name it has, where you have some weaker backup behavior that's guaranteed perhaps. So the sort of typical examples are you have a dynamic control system, an adaptive control system that you can't guarantee. But you have a guaranteed, simpler control system, and you know what its control envelope is, and you monitor where you are. And you let the adaptive system have control until you get to the edge of the area that the simpler system can control. And if you get to that edge, you hand control back to the simpler system. You know that it can manage that. If you go outside, you don't know that it can. So that's the idea of the simplex architecture. You hand control back to a simpler system. And, well, it's pretty obvious. It's not a blinding piece of insight. You can build systems that way. The problem comes, at the last ditch. So in the case of Air France 447, while they were high up, they had ice in their pitot tubes. If they could have got lower down, the ice would have melted, the plane would have recovered. But while you're high up with frozen pitot tubes, you have no data, no air data. You don't know what the speed of the air over the wing is. And without that knowledge, there's no safe way to fly the plane. You have to know that fact. You can sort of try to estimate it from knowing your ground speed and knowing what you knew previously about the movement of the air, whether you were in the wind or not. But there's no guaranteed way of flying the plane safely without air data. What's supposed to happen is the pilots hold constant pitch and thrust, and you could have automation do that. In fact, the Airbus that crashed did go into thrust lock, but the pilots then took it out. So, large disk behavior might be quite hard to justify, but again, maybe not difficult when you say no worse than human.
So, just a quick question. No worse than human can be also formulated as a assurance case.
Yes, and there's a probability, but very hard, of course, to justify. All sorts of ethical considerations and so on. There are things we forgive people, mistakes we would excuse in a person that we wouldn't excuse in a piece of automation. So it's got to be much better than human, I think. But there's some space here, some wiggle room. So, last slide, I think, conclusions. You've got a pretty good story for current systems. Breaks down for these imminent systems, like automated driving. There's some ideas for how we can try to rescue it. Monitoring is one of them. Another is that maybe these more advanced systems aren't so different as we thought. That a neural net isn't a totally opaque, unknowable thing. But, it is, after all, just a piece of software that works in a certain way, and it can be analysed, by modern SMT solvers and so on. And so there's this promising work. I know of work at Stanford and Oxford, here at Fortis. So it may be that some of the, foretelling of doom is unjustified, that even if things have neural nets in them and other systems based on learning, and, other currently opaque methods, they won't be opaque for too much longer. We'll be able to understand them. Or there could be a totally new approach, and there could be a totally new approach. I mean, my ideas aren't very original. I'm an old man. So young people might come up with new and better ideas. I think one of the key things is this notion of indefeasibility. It's what is the sort of bedrock guarantee that we have to think of everything. We cannot give that up. Okay? And I would be very reluctant to think that we should say these systems are so complicated, we can't think of everything. We'll just do the best we can. That's I would like to be on TV explaining that to grieving families. That we did the best we could, we didn't do the rest. And so I think we need to retain indefeasibility. That's to say, we do need to do the best we can to think of everything. And now I'd be interested to know what you think. Thanks very much. Apologize for going over there. 2 minutes.
So any questions? So I think we have plenty of questions by the time we are talking. So maybe...
Yeah, we had a good discussion yesterday as well.
Yeah.
Okay, it's not a real question, but then since you asked the question in the last slide, what do you think? I just to say my day, I agree with you that should really retain indefeasibility, even if it just amounts to actually saying at one point, okay, maybe we just reduce the strength of the evidence that we could, because here we have no other choice. But indeed, we should always try to keep in mind all of the possibilities.
Yeah, so one could say, I've thought of this, but I can't think of a really good way of justifying it. So I have essentially no evidence, but I have at least thought of it. And, I'm keeping an eye on it.
And also what you were saying before, so trying to have is this a suggestion on the organization that you should have some people who come and try, so external people who try to basically contradict what the system engineers are doing, or all the engineers. How do you envision this concretely somehow? You suggest...
So, that's a very good point, because as you say, it's really hard to imagine how that's going to happen, right? So, in current aeroplane standards, for example, 80 odd things you have to do, some number of them, I forget what number, like 30 of them, have to be done with what they call with independence at the highest levels. And what that means is that the team that assembles and adjudicates the evidence is different than the team that develops the stuff. But that's still sort of within the same company. It's going to be fairly cooperative. Whereas for full-on dialectical challenges, you need argument, genuine argumentation, genuine confrontation, I think. And that's really hard to do in most engineering contexts, right? It's really difficult. And so that's why I think it may be best to do these things at an industry level, where you have standards that are hashed out in contentious meetings, where people aren't embarrassed about really attacking other ideas. Going in and attacking someone else's system is I guess They do it to some extent for security. You invite hackers in to try and break into software. But it's not quite the same as actually having, you know, verbal argument where you, this is a dumb way of building your system. Why did you think of that? Oh, what about this? So I think it's, you know, it might be an achievable ideal to have strongly dialectical examinations of individual systems, and that one should do it at the one level back. Develop agreed standards, agreed templates for assurance cases where you argue it out that level.
The parallel with security is very interesting actually. It's true that we see more and more companies who are hiring hackers,
yes,
just with a special purpose of attacking it.
Yeah.
We could imagine something similar actually for safety.
You could. It's an interesting difference, by the way, between the European and the American airplane certification approach. So in Europe, when you want to get your airplane certified, you pay some money to EASA, and they send independent people to go and look at your evidence. In the United States, that work is done by people who belong to the companies that develop the stuff. They're called DERs, Designated Engineering Representatives. And so they work for Honeywell, Rockwell, and Boeing, but they've sworn allegiance to the FAA. And the argument is, only people who are deeply embedded really understand enough to pose the real challenges. Okay? And the people who volunteer to be DERs generally, you know, have that sort of attitude. They're people who really like to be, you know, thorn in people's sides. And, you know, so they're often, you know, tough people. And so, you know, it sounds corrupt when you first explain it, but there's a reason why it's done, and it might be better than having external people who are further away and don't understand all of the ins and outs that the deeply embedded engineers do. It's very, you know, it's hard to find a good answer.
It's actually very interesting because exactly this, like I was thinking a couple of times, maybe it would actually be better instead of having the current system in Europe and with EASA that you contact only at the end, to actually involve them from the beginning in the development. Of course, no company would accept such a thing, but
that's interesting.
We need to do it differently.
Because again, in the United States, the FAA does it throughout development. They have what are called stages of involvement, I think is the term that's used, and where it's, you know, and it could be different people at different stages. This is one argument they have, that they end up redoing a lot of stuff just because the personnel have changed. But you know, again, it is meant to be done throughout the life cycle. Yeah.
You could include this actually in your Bayesian network before. That is the probability that the assessor is making a mistake or not making the good sample in the...
Yeah. Building a fully accurate Bayesian model, of course, is very difficult, but I think it's valuable to have played with some. It tells you what sort of things seem to be powerful multipliers.
I mean, the indefeasibility seems to be feasible for technical systems. It's already getting harder with relatively simple systems like airplanes because there's a human in the loop. I think already there, maybe the indefeasibility argument breaks down. I think you gave an example of that, of the AF-447, where the pilots behaved differently than probably anticipated by the engineers.
Right.
And probably gets impossible with what we call open environments, right, where everything can happen.
Yeah.
And still, I mean, it might still be feasible for on the work that's going on here, work with these learning systems, because we can still say something about it. These are technical systems in the end. But there might be kind of a hybrid approach, right? We just drive it to the limit, but something else is needed for open environment. Everything can
that could be true.
Where a Concorde and a DC-10 can meet on a runway through some piece of garbage.
Again, that's meant to be something you take care of. There's a reason why they sweep the runway. You know, it has been thought of.
Yeah.
So the example that one of the NASA guys, Michael Holloway, uses is construct an assurance case for one of his teenage son's friends driving them all to a party. Okay, so you know, how do I know that this guy is a good driver? Okay, and how you can't possibly get indefeasible knowledge of that, right? And so you know, I find that quite a challenging case. One is that this isn't something for which you construct an assurance case. Assurance cases are about technical design systems.
Taking into account the environment.
Yes, taking into account the environment. And so that's to say the teenage driver. In the case of Air France 447, for example, you could argue that, and indeed in most cases where the pilots are blamed for causing the crash, in fact the design of the human factors and other aspects, the larger aspects of the system, are such that they were not helped, to say the least, by the design of the system. So, I don't want to blame the guys for things we don't know how they felt, but it's possible that they reacted the way you would try to react at lower levels, which is in an Airbus, it's safe to pull back on the stick, because the protections will then deliver maximum performance. When you do that at altitude, when the autopilot is already disconnected, you no longer have the protections, and so you can stall the plane. And so they made a mistake by doing that, but you could argue also that the design of the system that has this amount of complexity in it, anyone is going to be in a stressful situation, right? Whether they panic or not, it's going to be hard to think clearly in this circumstance. And maybe it shouldn't be designed that way. Either you leave the protections in, or there's some really strong feedback that tells you it's not there. Who knows? But yeah, you should anticipate. To be indefeasible, you have to sort of anticipate really unlikely stuff and try to deal with that as well as the likely stuff.
I wonder if the problem is actually that we can imagine by looking at the design some things which bring some trouble, let's say, and then we automatically try to think how could such a thing happen. And actually, maybe for indefeasibility, that's the problem. We should not start to try to imagine this, because we should assume it's always going to be anyway cases which are unimaginable. So we just forget this step, which we tend to do naturally, and say, okay, forget this.
Yeah.
Imagine it can happen.
That's right. That's right. Yeah, this state has occurred.
Yeah.
Without trying to imagine how it could have come about. How do I deal with that state? Yeah, that's a good idea.
So in a side remark is that this kind of deduction experiments are much more successful in making a system safe than testing. Is there evidence for that? Argue that that's true, because right now all systems I know of, they are basically being verified by testing. Of course, there's some thinking going on too, but 99% of it is testing.
I imagine it's a bit like what stories they tell about chess players and Go players, right? That the simple-minded mechanical chess players and Go players just search some vast space, treating it more or less uniformly, whereas the skilled human players, and now the deep learners, ignore most of the plays and focus their attention on where the action is. And I think these Gedanken experiments, one can focus on where the action might be, whereas just running tests, you're going to be driving the car around the street and seeing the same thing over and over and over again. You're not going to see the difficult cases very often, whereas the idea of thinking about things and maybe doing model checking and other, or mentally equivalent to model checking, does force you into basically all reachable states.
So I have one question. So the idea that you presented here is well valid. For example, from my personal perspective, for systems that will last for a very long time, where you have a lot of hours to do the things. But when I think of space, so say that we're now preparing a spacecraft to Mars, and then it only takes a 3 months mission. What is, for example, how could all these kind of arguments be applied when I just have all these kind of short-term missions, one-time missions?
Yeah, so they're one-time missions, but they tend to be very long, right? Multiple years. So it's very interesting. I was giving a talk at SRI last week, and the former director of the AI Center gave me a newspaper clipping about some Russian spacecraft that had just drilled into Mars. And one of these sort of absurd errors, how did they miss that? And of course there are numerous American and European missions that have made the same flaw. And I once asked a NASA guy about that. Why don't you just model check it, and find, this is one that landed with without putting its legs down and firing its retro rocket. He said, there's a billion things you could try to check, and how can you actually do all of them? And he said what makes much more sense is to try and basically do adaptive control, to project forward a few minutes from where you are now. And on board, you try to calculate all of the reachable states, and is there anything that could be a bad thing now? So that makes a certain amount of sense, you know, this sort of receding horizon adaptive control, where rather than just control, you're also doing hazard analysis. You're trying to anticipate all the things that could go wrong. So I have another story, okay, and different set of papers, on how one might build self-assembling systems. Where systems that have never met each other before, you know, say an infusion pump for this and an infusion pump for that, come together by being plugged into the same patient, and you want them to work together in a way that's safe. Well, they've never met each other before, so they have to sort of exchange some information and calculate safe behavior. There's lots of ideas for how you can do that in a fairly rigorous and controlled fashion. But you can imagine a slightly more aggressive scenario where you actually have to do some of the hazard analysis at the time you plug these things together. That's to say, the system itself has to have its, you know, its model of the world with maybe big uncertainties, and try to calculate, is there any bad state out there that I might be able to reach, and if I could, what should I do to make sure I don't go there? So maybe your space mission can have an outer loop safety controller that is doing more than just checking, more than just monitoring for known bad things, you know, but actually trying to do more of I call it runtime certification. You're doing something close to hazard analysis, exploring all of the possible near states with respect to very uncertain models of the world. Are any of them bad? If they are, steer away. Now, would you actually want to build one that way today? Be a gamble, but worth a try.
Good. Then I think that let's thanks John for his very insightful talk again, and let's close the session.